SN1 reaction is the first order kinetics. Reaction rate only depends on the substrate concentration. The concentration of nucleophile, the one that is finally formed bonding with new groups, is not relevant to the reaction rate. And that's because the first step, it involves a slow formation of a carbocation. The carbocation, we find out is tertiary is more stable than the secondary, and the primary is least stable. And with a more stable carbocation, the reaction activation energy is lower, so you have faster reaction. So the reaction mechanism, it have the key step, it is forming the carbocation. The substrate with leaving group, it has to be a very good leaving group. And that way the leaving group energy is low, and hopefully you have low activation energy. After the leaving group with long pair electrons left, the remaining carbon missing one electron becomes a carbocation. The carbocation stability is different. More hyperconjugation with more LQ group attached to the carbocation is more stable. So with the 3-methyl group carbocation, it is one of the most stable carbocations. And the very last step is very quick. Nucleophile that is surrounding in the solution will attach to the carbocation, give us a final substitution product. And hyperconjugation, the activation energy. This is the last time we show you the difference, the different degrees of carbocation with different number of LQ group. The more substitution give you lower energy carbocation. Since the carbocation is low energy, the activation energy is also lower because of the Hammond postulate. Okay, we have more stable carbocation, intermediate. Then the activation, the transition state also have a lower energy, which give you a lower activation energy, faster reaction. The primary carbocations normally do not form. Okay, do not form, too slow. The primary substrate, as you remember, is highly preferred in the SN2 reaction. Is the second order single step substitution reaction. Okay. The SN1 reaction stereochemistry, the spatial relationship of those final product, it is different from the SN2. SN2 is the inversion because the nucleophile attacking from the other side of the carbon, and they remove the to kick out the leaving group. The SN1 reaction, since going through the carbocation intermediate, the carbocation, it is high energy, but it can exist for a brief moment. So that means it gives us time for the nucleophile to attack from both ends. Okay, either from the red end or the blue end. And from these two opposite sides will give you the racemic, which means the final reaction product at this chiral center. You have equal amount of both product. The R product and the S product is about 50-50. So the stereochemistry for the SN1 reaction is completely different, and oftentimes this is the tool. This tool shows chemists, is this reaction taking place goes through SN2 or SN1 reaction? Well, how do you know? Well, let's do make the substrate where the nucleophilic attack, make it a chiral, and then go through the reaction. If the final product end up racemic, means equal amount of both RS, that means it's SN1. If your reaction have only the inversion product, that means SN2 reaction. So the stereochemistry, it is the evidence to show us does the reaction go through SN1 or SN2 reaction. But with SN1, there's a chance of very slight tendency for the inversion. This is because when we have a substrate with good leaving group, after leaving group is dissociated, form a carbocation, it has a negative charge. It still might be attracted to the carbocation. Okay, so when this leaving group attract to the carbocation, that's make it difficult, more difficult for the nucleophile to attack from the same direction where the leaving group is leaving. Okay, this is a little conflict. So because the leaving group is still temporarily loosely attached to the carbocation, the final product, the inversion, which nucleophile attack from the other side, opposite side from the leaving group, have a slight preference. It has a slightly better chance of forming the final product. Whereas the nucleophile attack from the same direction where the leaving group is, that'll make it a little difficult because the leaving group is still kind of getting away. So we would normally consider to just get a perfectly racemic mixture. You get an equal amount of RNS product in the final product. But in reality, there's a slight preference for the inversion because nucleophile attack from the other side slightly better because without any interference from the leaving group. Okay. So there's a summary for the SN2, SN1 reaction. The mechanism is completely different. The SN2 key step is a one-step reaction. Attacking and leaving happens one step. So we have two arrows. Okay, the SN2. SN1 reaction in the key step, it is have two separate steps. The bond breaking, bond forming is in two separate steps. The slow step is the bond leaving, the bond breaking group, bond breaking step. High energy form carbocations. And since this one, the key step have a one reaction intermediate, you have a little valley in the between two peaks in the potential energy diagram. Kinetics, of course, difference. The rate of reaction compared with the reaction site. The reaction site where the carbons attached to leaving group. It depends on the degrees of carbon. The SN2 reaction. SN2 reaction, those atoms nearby the reaction site really get in the way of nucleophiles to attack. So the smaller groups, then it's a faster reaction. And that's why the methyl with all the hydrogens is no hindrance, it's the fastest. And the tertiary essentially will not go through the SN2 reaction. Okay, tertiaries will not don't like to go through SN2 reaction, and because the huge hindrance from the 3 alkyl groups that is in place of the hydrogen. Stereochemistry inversion. The SN1 reaction, you can see the depends on the carbocation stability. And the carbocation stability because of hyperconjugation. Tertiary give you most stable carbocation, so the fastest reaction. And the secondary. Methyl and primary do not go through SN1 because carbocation is too high energy, unstable. So these two are the stereo effect. It is just opposite between SN1 and SN2. So this is actually we need to always keep in mind. The final stereochemistry SN1 is a racemic, so basically have a roughly equal number of equal amount of inversion versus retention stereochemistry on the chiral center. And okay, so this part we continue with SN1 reaction with alcohol. This slide I modified from the original, from the one you last downloaded. The alcohol reaction with a hydrohallic acid will give you the alkyl halides and water. So this is also a substitution reaction. OH replaced by the halide X. This reaction is different from the SN1 we just mentioned before, because the OH group, it comes from a weak acid, basically hydroxide, a very strong base hydroxide. So being a strong base and come from a weak acid is a very poor leaving group. The leaving group for SN1 reaction is very important. The better leaving group is easier to form carbocations. And what makes a good leaving group, it is the anions, once they leave, the anions must be very stable, which means once those anions really want to exist, do not like to combine protons or whatever. So the weak base, which come from the strong acid, are the better leaving group. Okay, so what make a good leaving group? It is they are the conjugate base from strong acid. So these are the strong acid, as you learned before: sulfuric, hydroiodic, hydronium. These are very strong acid. And so the conjugate base of those three acids, this is bisulfate ion. Okay, bisulfate, iodide, water. These are a very weak base. That means they can be very good leaving group. Well, with OH in the alcohol, OH by itself is not a good leaving group, but this is because hydroxide is a very strong base, so it's not a good leaving group. What makes this reaction taking place? It is we can add in the acidic condition, so that the alcohol can be protonated, because the alcohol with a long period on the oxygen can be base, its base. Once protonated, add a proton on the hydroxide. This will become becomes a protonated alcohol. Then this portion, you notice this is just water. And as we know, the water is a very good leaving group. So therefore, the alcohol will reaction with the hydrohalide acid, reaction going through the first protonate, because acid, protonate becomes protonated alcohol, and then the water becomes good leaving group, dissociate. And after water left, we form a carbocation. So the from this on, the following couple slides is dealing with SN1 or SN2 reaction that has more than, there's one step that is make the poor leaving group become better through the protonation. So this is the first one we would consider. Let's find a better color. Okay. So for reaction, the with the protonation, such as the alcohol becomes a halide. The alcohol is not good leaving group, but with the acid, we will have a first step form the it protonated by the acid. So the reaction, the first step, and this reaction is the hydrochloric acid dissolving water. So the acid, okay, the acid with HCl in water all become hydronium, okay, in the aqueous solution. First step, it is hydrochloric acid dissociating water, give hydronium ion. And so first step, the alcohol need to have the protons attached, becomes so that water becomes a leaving group. Very first step is the proton transfer. After this, we get the first reaction intermediate. So when you write down the reaction mechanism, you basically maintain all the other carbon structures same. You change only one part that reacted. show all the charge. Show all the charge. The charge better put in a circle. That'll make it easy to locate. Okay, so that's the first step. And the first step, this is a proton transfer, or I like to call it protonation, so adding proton to something. And then the next step, this is tertiary carbon. Okay, tertiary carbon strongly prefer the SN1 reaction because with good leaving group water, the remaining carbon becomes a carbocation. Trigonoplanar geometry. So that's the, we lose water if you write down the inorganic product, which is losing water. Normally we focus on only the organic, the carbon structure, the main bulky structure. And then, okay, our final goal is getting to the alkyl chloride. And in the solution, when the hydrochloric acid dissolving water, we have a hydronium, and the other key, but the other anions in water, it is chloride. So from this step, it's simply just chloride that is already in the solution, negative charge. It attack, so the chloride as nucleophile attack the carbon, and then you're done. So this SN1 reaction has one more step, is the first step, protonation or proton transfer. This step is extra. The actual SN1, the forming carbocations here. But to make the leaving group easier to dissociate, it needs to go through the protonation, adding proton to the weak base OH group in the alcohol. So the three steps are summarized as the protonation, forming carbocation, and followed by the last step, nucleophilic attack. And so this is SN1 reaction just because the alcohol is a tertiary alcohol. Tertiary alcohol, which have a tertiary carbon, and a carbon linked with OH. So keep in mind, when you have OH group being replaced by some other group, it always has to start with the protonation, become a better leaving group. And especially for SN1 reaction. In the SN1 reaction, the dissociation of the leaving group is critical. Easy leaving group make it easy to form carbocation. And there's another SN1 reaction. By the way, this reaction looks different from the other. Okay, this, oh, the title, I'm gonna make a mistake. So the actual reaction is reversed. Sorry, just that. By the way, this reaction, if you look, tertiary chloride with water becomes alcohol and HCl. This looks exactly opposite from the previous slide. But this reaction does happen. The reaction happen is simply because this reaction and previous reaction are the opposite. It's a reversible reaction. It depends on what is the concentration of the reagents. It will push the equilibrium to the right or left. Okay, so depends on the concentration. This is the situation when you have an abundant amount of water. Okay, abundant amount of water in the reaction. And the previous example is you have abundant acid, and acid protonate alcohol. Anyway, this slide goes through a different mechanism. You have only the chloride, just there's no OH, so you do not start from protonation. Instead, chloride by itself, it since come from the strong acid HCl, which means chloride is very stable, weak base, good leaving group. Okay, chloride is a good leaving group. So since the chloride is good leaving group by itself, the first step is very simple. Just have dissociation. And after dissociation, leaving group depart, it forms the carbocation in the first step. The other product, it is chloride ion. So you lose chloride ion in this reaction, minus chloride. And then our final goal, the product is form the alcohol. And with water as a solvent, of course, the waters they are good at nucleophile. They are fairly, because the long pair electrons on oxygen. And so the next step, it is just that the water as the nucleophile. It uses a lone pair to form the bond with carbon. Okay, so now we're getting interesting. Now we're going to this carbocation with oxygen, and the oxygen still have a 2 hydrogen attached. Okay, this is very important. One lone pair used to form bond becomes a bonding pair, but there should have another lone pair on the oxygen. And since the oxygen lost one lone pair, so the charge goes up, become positive charge. So that's basically the forming the a protonated alcohol. This is actually a protonated alcohol. And finally, to get to the final product alcohol, you need to lose one of the protons. So how to lose it? Again, the reaction takes place in water. Okay, since in water, and the water can act both like an acid and base, and the water can, with a lone pair, take away one of the protons from the reaction intermediates. Okay, so the reaction takes place. It is water. Use a lone pair to take away. This is typical proton transfer. It's just like in the chapter 6. 2 arrows. Take away one proton. So deprotonation. This is the last step, deprotonation. And after deprotonate, it becomes final alcohol. So this is the 2 different reaction mechanisms we saw, the SN1 substitution reaction. One is from alcohol, become halides, and this is the opposite. And each one have more than just, even those SN1 reaction, it should have 2 steps, now have 3 steps. So this slide and last slide, they are very different in the reaction mechanism. They kind of looks like opposite, by the way. They looks like opposite. And even if you try to write down the reaction steps, they looks almost perfectly reverse. Okay. So these 2 is good comparison. The carbocation, there's a major change in this slide compared with the old slide. So if you open the new PowerPoint file, you can see the major change. The carbocation can go through rearrangement. This is in the one of the 4 arrow pushing patterns we saw in the energy and the mechanism chapter. Okay, before the it should be chapter 6. Okay, we saw the carbocation can rearrange. So either the hydride shift or a methyl group move around, change location the carbocation. Since SN1 reaction it goes through the carbocation. The hydride or methyl with electrons can move, but it's not just for no purpose. The reason because such a rearrangement oftentimes lead to a more stable tertiary carbocations. So the 3R group the rearrangement should eventually lead to a more stable carbocation. And then the carbocation, since it's more stable, it will have the nucleophilic attack, give you the final product. And so the rearrangement, oftentimes when you look at the questions, look at the reaction, you notice there's major change in the carbon structure. When you see the major change in carbon structure from the beginning reactant to the product, that's the first thing you would suspect. There must be a rearrangement. And the rearrangement in our class almost always going through the SN1 reaction, the carbocation reaction. And it must through carbocation. And the carbocation typically from the SN1. Later, the next time we'll go through elimination. Elimination can also go through the carbocation. So anyway, this is the rule I find out over observing so many examples. This is the kind of empirical rule, which means it is based on the fact, based on the experiment results. When you go through the formation of carbocation, if the initial carbocation is next to a quaternary, which means a carbocation next to a carbon linked with 4 carbons, then one of the carbon, the methyl group, would be able to shift, move, form more stable carbocation. And so this is a methyl shift, give you more stable tertiary carbocation. The second rule, when the initial carbocation is next to a tertiary carbocation here, and when you have this carbon, this kind of carbon, this carbon have a 3 carbon link, and there's 1 hydrogen. Then this hydrogen, if relocated to this carbon, it'll form the stable tertiary carbocation as well. So that's the pattern we notice in the organic chemical reactions when there's a nucleophilic substitution. And so this is the reaction. Okay, this is the reaction. That is the first situation. It happens because you can see there's a bromide and the secondary, and the solution, you have a sodium chloride and aqueous and water in the reaction. The first step, notice the bromide, and this is carbon, is a secondary carbon. So the reaction is not an SN2 reaction. And main reason because chloride is not a strong nucleophile. And so the first step, it is form a carbocation. Leaving group, bromide left, and you have a carbocation. Once the carbocation forms, you notice it's next to a carbon that is quaternary with 4 carbons attached. So in this situation, it'll be the first scenario. Carbocation next to a quaternary carbon. So the methyl group shifts to this carbocation, form bond with this carbocation with a pair of bonding electrons. And after this, we will have the methyl group now is here. Okay, this is a new methyl group. And this carbon lost the methyl group with a pair of electrons. So the carbocation formed here. And this part did not change. So you can see carbocation next to quaternary carbon. Methyl group, this methyl group, it shifted, changed location to a different carbon. The end results, so you have more stable carbocation, being tertiary carbocation. And then finally, the very last step. The very last step, this solution have sodium chloride and the solvent water. Chloride being the nucleophile. Attach, more like attach. Okay, I should not write down the nucleophile. Should we just chloride? Okay, just chloride. So there's a chloride, long pairs, negative charge, form bond with a carbocation. And then final product. The final product is kind of crowded, but we have these two, the alkyl part, no change. But now we have chlorine attached to the main. So this is the final product. This reaction, rearrangement, because the carbocation is more stable, this will be the major product. Another product, it is where the after forming carbocations, no rearrangement, and just chloride attack on this carbocation. This product is actually the very, very minor product because the carbocation is not stable, high energy. So keep in mind the carbocation might form and cause a rearrangement in the SN1 reaction. So this is the comparison between the SN1 and SN2. We saw the other chart dealing with the kinetic, the activation energy, kinetics, the water order, reaction, and so forth. This is more the summary between these two. We notice the proton transfer. When you have a substitution reaction, and you'll notice the leaving group is not good leaving group, like OH. Protonation is necessary. Okay, so when you have a poor leaving group. Basically, OH group. This is the main leaving group. Especially when the condition mentioned about acid, yes, that was the first thing you would think about, because the acid abundant in the solution, there's always an equilibrium between the alcohol and the protonated alcohol, and when there's abundant acid, it'll push the equilibrium to the protonated alcohol. The second one, look at what the reaction mechanism. The reaction mechanism can be SN1 or SN2. Remember, SN1 really prefers when the carbon is a tertiary carbon with leaving group. And when the carbon is primary, then it needs to go through the SN2 reaction, just because carbocation is not possible. Rearrangement is always as in the SN1 reaction because it forms a carbocation. So tertiary, forming the carbocation, and then rearrangement will tend to give the tertiary carbocation, make it more stable. Once we decide on this, we decided SN1 or SN2. Then we know the stereochemistry. So the racemization, forming racemic, equal number of R and S product. SN2 is a specific. If you start from chiral center in the SN2 reaction, the end product is still chiral. It will be inverted chirality. SN1 is attacked from both sides, so that's no stereochemistry specific. So that's SN1, SN2 in comparison. The real, we have to do the after homework to really get a practice to understand better. Some of the reactions, when you have a primary alcohol, and so this is a primary alcohol and become a primary halide. The primary alcohol, first OH is not good leaving group, and because primary, it will not go through carbocation. It will have to be the SN2 reaction. And also primary is just favors SN2 reaction. It's good for the nucleophile to attack. But this reaction is still difficult because OH is not good leaving group. You cannot just have some halide just come in, kick out the high OH. Carbon with the OH bond is very strong. So again, we use the protonation first. With the acid, turn the OH group to a better leaving group, like water. So with a strong acid, notice this is a sulfuric acid with water. That means there's abundant hydronium ions as acid. It can give protons to whatever base in the structure. And the alcohol lone pair electron on the oxygen will be good base to attack. This diagram reaction mechanism do not have arrows. So the arrows we will have to add. Very simple. This is the first arrows we practice on, proton transfer reaction. And after this, it takes protons, becomes the alcohol with extra proton. We call it protonated alcohol. And you can see this looks familiar. Water. It's good leaving group. So, but this step, very important. It did not form a carbocation. It's unlike the previous two examples. So it did not go through carbocation just because energy is too high to become carbocation. Instead, the reaction goes, the nucleophile in this system, we have water, there's acid, there's a sulfate, chloride. Among these three, the chloride is better nucleophile. And the better nucleophile will attack from the backside. Okay, very important. For the SN2 reaction, nucleophile attack from the other side of the leaving group. And then this is the final SN2. This is a key SN2 step. Is a synchronized concerted bond forming and bond breaking happen at the same time, and give us the final product, alcohol. So when you write down reaction mechanism and form a carbocation, I know the carbocation sounds very cool. Wow, you have a carbon form positive charge. Well, doesn't always happen. You have to look at your substrate. If your substrate, the leaving group on the tertiary carbon, then yes, it'll be the carbocation intermediate. But otherwise, if the carbon is primary with the methyl group or ethyl group, one group on the alcohol, the carbon is the primary, then it should go through the SN2 reaction. So in a sense, the SN2 with the protonation, it has only the two steps. It saves one step from the SN1 reaction. So keep in mind, if the SN1 reaction, it looks like there's number one in there. It's a first order reaction, but have one more step than the SN2 reaction, because it has one more reaction intermediate, the carbocation. SN1 reaction has one more intermediate, which is carbocation. So there's some more examples, and again, you look, this is a very good reaction, and this compound that we call epoxide. Several weeks later, when we deal with the ether, when we discuss ether, we'll see this compound again. It's epoxide, highly reactive, and can open the ring, can easily form polymers. In nowadays industry, this epoxide is very useful. And even the glue, the epoxy glue, is a 2-part glue we can buy from store. Very strong bonding, and we use epoxide as one of the ingredients. So this alcohol, this is actually epoxide. It under acidic conditions, rings open up, and one more OH come in. This one more OH come from the water. This reaction actually is just the epoxide react with water, but it has to happen with acid. So whenever you see the acid in the reaction, always think about somehow there must be some lone pair in the reactant that take proton from the acid. And this reaction, it is nucleophilic substitution, but end up this nucleophile and the leaving group both stay in the same structure. Okay, no bond actually. There's no parts dissociate from the reactant, unlike the previous substitution. Okay, this is so the first step. We have abundant acid. The reaction happens is the protonation. Again, you have a lone pair on the oxygen, so that's the base. It takes proton from the hydronium. So now becomes a protonated epoxide. Again, this is a OH, but this oxygen is bound with 2 more bonds, 3 bonds. Even though this does not look like has a water as leaving group, but you can see this part. This part itself, it is alcohol if you don't look at the charge. So this entire, the blue circle, is a leaving group. But leaving group is only break this bond. This bond breaks. This bond do not break. So this OH still stay in the same structure. Okay. But again, this carbon is a primary carbon, have 2 more hydrogens. It cannot form a carbocation. So the step to break the bond must have the nucleophilic attack happen at the same time, which is water. Okay, remember water is added to the epoxide in the end. Water here, this is how the water gets in. It attacks the carbon and at the same time breaks this bond. So nucleophilic attack and the bond break, the leaving group bond break happen at the same time. That's SN2 reaction. And after this positive charge disappeared. It's actually here. This part is the one that is breaks. And the nucleophile was neutral and now form bond with a lone pair. It gains a positive charge. And so basically this is you can see the similarity between the final product and this intermediate. It's almost the same structure. Only difference, this OH, there's one extra positive charge, extra hydrogen. So to remove the final positive charge of hydrogen, which is basically H+, we just need a base. Again, this reaction happens in water, and the water is the largest amount of base, even though it's not a very strong base, but it's the most abundant. Water molecules will take away the proton. So the very last step, it'll react with this proton and break the bond. And that will give us the final product. After the alcohol lose 1 proton, give us the final product. And so you can see there are 2 steps has a proton transfer. It has both protonation and deprotonation. We start from a kind of ether. So need to gain proton first. This example is more difficult, more advanced example, because it actually breaks the ether bond. start from ether and becomes alcohol. And notice this is a SN2 reaction because this carbon is primary. This is primary carbon. So it will not go through the carbocation. Okay, so these are some examples of see how does the reaction takes place, and this is the reaction. All the arrows are pretty much I just did in the last slides. This reaction, it is exothermic, and also the final structure, there are more freedoms in the whole structure compared with the reactant, more freedom. So is exothermic, and the entropy, the entropy actually decrease mainly because there's a water. These two are the reactant. After reaction, the two reactant molecules combined together becomes only one molecule. It's a combination reaction. That's why I have a negative entropy change. So anyway, the main focus is on how we kind of appreciate the reaction like this. I don't see any, we have any example homework deal with this kind of reactions, but it's kind of fun to think about how we can use a protonation to form better leaving group. And towards the end of the reaction, if the intermediate have a positive charge and extra hydrogen, use the base that in the solution to take away the proton, deprotonate to get to the final product. And so this is the also SN2 reaction because you have a halide, and this is primary halide. And the end of the reaction, because the reaction with the alcohol finally end up getting ether in the final product. So this reaction takes place. Halides, and this is the alcohol. This halides, by the way, the iodide. Iodide is a very good leaving group because iodide comes from one of the strongest acid in aqueous solution. HI was one of the strongest acid. So iodide is great, very stable base, very good low energy leaving group, easy to leave. But this is primary carbon, so you cannot go through the SN1 become carbocation. So how to do that? Well, the alcohol, even though it's not a good nucleophile, but when you have a good leaving group, it still helps. Then the first step is simply just is SN2 reaction in the first step. First step is kind of the alcohol latch on, combined to one molecule. But once you get down, you notice the lone pair from the alcohol form bond. And this oxygen lose the lone pair, okay? Because from the lone pair becomes shared pair, lose one electron, positive charge forms. And so you can see the now you look at the final product compared with the intermediate, almost look the same. That's great. That's a great step. First step is hard to see, to think of, to come up, because once you form first step between this and this is so much alike. Essentially, you are in the you get on to the right direction. Only difference is now the intermediate has one positive charge, one more positive charge, and one more hydrogen. This is easy to deal with because just need some base to take away the proton. And look at the reaction condition. What kind of base can take away the proton? By the way, this reaction so far, there are iodide in the solution as well. There are iodide in the system. And there's the alcohol as a solvent. To take away the proton, we need some kind of a stronger base, okay? Because iodide is base, alcohol is a base. Which one's a stronger base? Well, iodide comes from very strong acid. Between these two, alcohol is a slightly stronger base. And also alcohol is abundant in the system. It's in the solvent. Iodide is just very small as a product. So between these two to compete, it is the alcohol as a base will take away the proton. So the very last step, just the alcohol take away the base, take away the proton. This is a proton transfer reaction. Take away proton, deprotonate, and will give us final ether as a product. So this reaction is SN2, not SN1, just because the leaving group is on a primary carbon. Okay. If you see the leaving group attached to a tertiary carbon and also with alcohol, the reaction most likely goes through the SN1 reaction. So that's the different reaction. This exam, this quiz that we're coming up, it is focused on the SN1 versus against SN2. So just keep in mind, primary, prefer SN2. Tertiary, go SN1. And maybe some steps needed to link all these, link them together. This is the last part discussion. It's actually fairly lengthy, and we have to dissect into the several aspects. How do we know this reaction is SN1 or SN2? It's always confusing. Okay, always confusing SN1 and SN2. So we break down the 4 topics when we decide which way to take place. The 4 main factors. The first one, it is the substrate, the one with the leaving group. Okay, this is the one with the leaving group. The nucleophile, by the way, substitution, nucleophilic substitution, the nucleophile eventually will form bond, but nucleophile not always in a slow step. So we discuss, we focus on substrate first. And talking about a substrate, there's a stereochemistry effect. We need to think about other very crowded, is a tertiary carbon with a leaving group or primary. Okay, so that's the thing we need to think about. When there are more alkyl group, the tertiary carbon with a leaving group. Because there are more carbon around, each carbon has a number of hydrogens. That'll make it difficult to approach by nucleophile. But instead, it's easier, more stable carbocation once the leaving group dissociate. So when you have tertiary, almost always is SN1. Sooner or later with SN1. And the second topic actually still relevant to the substrate. It's still on the substrate. The leaving group. Is the leaving group easy to dissociate or not? We just see the water is much better leaving group than the OH group. And then the strength of nucleophile. Okay, this is the not always critical, because as you can see, the SN1 reaction, nucleophile is not involved in the slow step. Only SN2. This is the critical for SN2. And finally, solvent. The solvent have some effect, and this we need to know. Not a major, not something major, but we need to be aware of. The first, the substrate leaving group. When we talk about the substrate, the SN1 reaction can benefit from the stability of a carbocation. And what to make the carbocation more stable, in organic chemistry, we have 3 different kind of, the 3 red ones are the groups that we need to be aware of. First one is vinyl. Vinyl is the carbon that are looking at. It has double bond with other. carbon. This is a vinyl group. Allele group. Allele group, if this carbons we are interested, it is bound directed to a double bond. This is an allele group. So it's all focused on which atoms is you are focusing on and how this atom bond with other carbons. Benzyl group, if you look at this carbon, the center of focus is linked with a benzene ring. That's what we call benzyl. We call it benzyl group. The benzyl group and allele group kind of similar, but you can see, because you can see the carbon of interest is linked to a carbon with a double bond, as you can see here. So benzyl group and allele group is very similar, and we can see from the carbocations, these two are very similar. This structure kind of asks about which ones the vinyl groups and the allele groups. Okay, so this is the first one. This is actually the benzyl group. Benzyl carbon, benzyl. And this is allele. Benzyl again, BZ. And this it will be the allele, because they are linked to a double bond, allele. And the vinyl carbons are these are vinyl carbons. These are the vinyl carbons. Allele carbons are circle. Allele and benzyl is very similar. And there's more allele. This is also allele. These are all the allele groups. Allele carbon. And this is also allele. Discuss on this, it will help understand the stability of the carbocation. Aerial is just a more general form of a benzene ring. If the benzene ring have some other group, maybe have here, maybe have here, maybe here, maybe here, then this we no longer call this benzene. In general, we call it aerial. It comes from the word arene. Benzene becomes the arene. So these are the unsaturated groups in organic chemistry. They, allele or benzyl, if the carbocations on those allele carbon or benzyl carbon, it becomes more stabilized. That is because the resonance, okay, because the carbocations formed can be stabilized by the resonance. So here's this example. This we call allylic. This carbon, the allele carbon, if the X is leaving group dissociate, carbocation will be formed here. It can be stabilized by the double bond. Same as benzene, the benzyl. This is benzyl carbon. Benzyl carbon with the leaving group gone, you have a carbocation here. It can form resonance with benzene ring. And when they have the resonance, this stabilization even stronger than the hyperconjugation. So this is how the resonance, after leaving group forms, it forms a carbocation. And the carbocation, it have a resonance. So this is arrow pushing we learned before, the resonance arrow pushing. Double bond moves, and so basically the charge shifted and bond also shifted. It becomes stabilized. Allele carbocation can be stabilized by the resonance. And with benzene is very similar. With this bond just dissociate is SN1 reaction. These are both SN1. Single molecule dissociate. The carbocation first form here, but the resonance, let's see, okay. All these resonance missing arrows, so it's good practice to show all the arrows. Okay, so you can see from here, from this carbocation become that. This bond, you can see this bond formed, where this bond becomes a single bond. So the arrow move must be this way. It helps form this double bond. And the benzene ring arrow pushings is actually all 3 arrows happen at the same time. And actually, sorry, I did too many arrows. Sorry. This one, the carbocation only here, so we need a couple more steps to get there. Okay, so we don't have these two. Only 1 arrow. Okay, 1 arrow move, get here. And next, we need to think about from here to become that. That's where we need more arrows. Okay, so from here to get to that, charge moves, so only 1 arrow becomes the different carbocation. And finally, the last step give you the final carbocation here. So you can see the benzene ring with carbocation has more resonance structures. Therefore, the stabilization is much stronger with carbocations. So basically, the allylic or benzyl carbocation is really preferred in the SN1 reaction. They are highly preferred. The vinyl or aryl, so the carbocations is a part of the double bond. Okay, this carbon is a part of the double bond. This is not a good situation because when you leave this with leaving group left, the remaining carbocation, it is part of the double bond. This is not stabilized. There's no resonance structure can stabilize this. So therefore, these two kind of compounds are difficult in the SN1 reaction. It's impossible in the SN1. It cannot be stabilized. The benzene ring, this carbon itself have positive. So the allyl, so kind of refresh memory, is when you have this allyl carbon. And with benzyl, the carbon that is outside the benzene ring is a benzyl carbon. These two stabilized, and therefore it is preferred in the SN1 reaction, not the vinyl or the aryl. So in our sampling assignment, we actually haven't seen that many the allyl or benzyl in the SN1 reaction, but we just need to know. Okay, the second one, leaving group. Leaving group, like I mentioned, it is a weak base by itself, and the weak base means they do not attract proton very well. They prefer to be separated, and since they are not attracted to proton, it's understandable to think those leaving group do not hold carbon very well either. So that's why the weak base or more stable leaving group, very weak base, stable anions, which means a weak base, are the good leaving group. And so they must come from a strong acid. Okay, this is kind of a twisted. Strong acid give you a weak conjugated base, which is good leaving group. It come from strong acid. The opposite, if you have a weak acid, then you give a stronger conjugate base. Conjugate will be stronger. Then it will attract protons, and it will also attract carbon. Make it not unlikely, make it unlikely to leave the carbon. So it's bad leaving group. Okay. And so the example of good leaving group, come from the strong acid. First, the acetate. Acetate is a very good leaving group. By the way, acid is kind of different because, as we know, acetic acid is not strong acid. But in organic chemistry, I guess there's some reason why the acetate, even though it comes from a weak acid, it turned out to be very good leaving group. nitrate, the nitrate ions, good leaving group. These actually, we rarely see them in the organic chemistry because nitrate compound oftentimes are explosive. So guess what? We rarely deal with them. Try the nitroglycerin, which is actually the explosive Nobel that find a way, discover a way to stabilize the nitroglycerin. And that's why he made a lot of money, and nowadays set up a Nobel Prize, we'll give it every year. Nowadays, these couple of days out, the Nobel Prize for Science has been announced one by one. And he's actually deal with the nitrate. The nitrate itself is a good leaving group because nitric acid, the strongest acid. This is the related to sulfuric acid, but it's organic, has organic carbon. It may not have, maybe hydrogen. If this is hydrogen, then this will be the bisulfate. This will be the bisulfate. That will be the bisulfate ion, which comes from sulfuric acid. So it's a strong acid. This comes from hydroiodic acid, strong acid. This comes from the hydronium. That's the strongest acid in water. So these are very good leaving groups, as we can see. The water, we have some discussion before. Bad leaving groups, we've seen this before. Hydroxide, bad leaving group. That's why they need a protonation. The ether with this is we call it mesoxide as a leaving group, is bad leaving group. Nitrogen, the amide come from ammonia, is a very weak acid. So these are all compound weak acid, not good leaving group, because they all come from very weak acid. And the hydride is one of the worst, weakest acid, not good leaving group. And so these are common leaving groups in organic chemistry. The halides, because these halides come from strong acid. And these are associated with sulfuric acid. That's why they are very strong acid, made in good leaving group. And there's one video that people probably see that. Maybe a video. Yes, there's a video about the leaving group. We kind of just ran low in time. Okay, let's watch this video and then just stop. The next topic is the nucleophilicity. So basically, how good a nucleophile is. The nucleophile is very important for the SN2 reaction, because the SN2 reaction, one is the main reaction, it is nucleophile attack, and the leaving group break at the same time. In SN1 reaction, nucleophile is not important because the nucleophile react in the fast step, react carbocation. And so the nucleophilicity, or how good quality of the nucleophile, it is based on the experiment. There's not so much. There's a little pattern into memorizing, but mainly just to have just memorizing. The good nucleophiles, very good nucleophiles, are the iodide and the bisulfide, and this is the alkyl siolate. This is alkyl siolate. So these are the good nucleophiles. And the RS minus alkyl sulfate. So it's a sulfur-based anion. And so when you have those ions, you can see these come from fairly strong acid. Stronger than many others. And also they are bigger ions, sulfur and iodide in the lower part of the periodic table, and so they are better in the nucleophilic attack. And there's a good ones, good nucleophiles. Bromide hydroxide, the alkyl alkoxide. Alkyl with oxygen alkoxide in the good nucleophile. Cyanide is a very good nucleophile because it bonds with carbon. It bonds with carbon to the electrophilic carbon. This is azide. None of all these, these are, we normally don't ask you to memorize. Okay, we don't ask you to memorize because in the reactions, you can see that those ions are present in the reactant. So those anions in the reactant or in the solution have a negative charge. They tend to attack the positive charged carbon in the substitution reaction. And the weak nucleophiles, these are, you can see the all of these except ammonia are negative charge. They all have negative charge, one negative charge. And negative charge being the better nucleophile is understandable because the nucleophilic attack, it has to be the lone pair attack the carbon. And with more negative charge, there's more lone pair available on this attacking nucleophile. So the weak nucleophile, they can be nucleophiles, but they are not very strong. And those are, you can see, they are neutral. Okay, you can see the carboxylate, which is here, negative charge. And the carboxylic acid, it still have a tendency to use the lone pair oxygen to attack the electrophilic carbon, okay. But much less tendency because it's neutral. Once you form the attack, and then it becomes positive charge, and that's kind of high energy state. So for the reactions, if you see the nucleophilic reaction, and with a good nucleophile, it tends to be the SN2 reaction. Okay, good nucleophiles prefer SN2. And SN2 reaction, the stereochemistry is inversion. Okay. The poor nucleophile, weak nucleophile, these are weak nucleophile. Weak nucleophile is not good for SN2, but can react in the SN1 reaction. And I can see the example previously, alkyl halides react with water, form alcohol. That's a typical reaction as going through the SN1 mechanism because the water is a poor nucleophile. And so the nucleophile, these are the one we, this over time, as you practice, memorize. What are strong nucleophiles? Weak nucleophiles, these we mentioned before. Fluoride is very weak nucleophile also, because you mentioned, we saw the halides except fluoride are the strong nucleophiles. So that's the organic chemistry. When we discuss the mechanism, is based on the fact, the results. The mechanism's hypothesis. Okay. We just need to come up with a hypothesis, best explain the fact. And so to keep in mind the reaction, we learned all these arrow pushings, and there are so many steps for some of the SN2 reaction or SN1 reaction. And especially the carbocation, okay, when there are SN1 reaction, there are more than one step, typically 2, 3, or 4 steps with the carbocation and SN1 reaction. So that is the carbocation SN1 is typically with the water as nucleophile. And so that takes some practice, get it memorized. Okay, by the way, I gave a 2 worksheet last night. Those two worksheets actually including they include the answer keys for some quiz questions, but you have to kind of go through all the questions to dig them out. Okay, so it's kind of tell you the secret. It is the some answer keys in that, and even some major question in the quiz actually is covered by the those two worksheets. So go through the two worksheet and practice and learn. The solvent also affect the transitions, affect the reaction pathways, SN1 or SN2, because the solvent, first of all, has to be a polar solvent because we're using many ionic compound or strong acids in the reaction. So the solvent has to be polar to accommodate those polar solute. And those polar solvent will interact with the reactant, we interact with the product, but more importantly, it interacts with the transition state. The transition state with the polar solvent, it can interact with both the carbon and the leaving group, and even the nucleophile for the SN2 reaction, SN2. So this can be very complicated, but we're not getting into too much detail. How does it affect? But as the organic chemists, we did numerous experiments. We found out the solvent, even they are polar, it can be further divided into the protic solvents. Protic solvent means is a polar solvent with the hydrogen attached to the polar oxygen. Because this kind of solvent, it can act like a weak acid, which means it lose protons. So this is what we call protic solvent. Water, alcohol are the examples. And this kind of polar solvent, they are in favor of SN1 reaction. This is very important. Polar protic in favor of SN1. Because when you have those polar protic, it can stabilize both cation and nucleophile in that transition state. There are many polar solvents, as you can see there. There are many polar solvents without OH group. These are called polar aprotic. The hydrogen will not be able to dissociate as a proton. So polar aprotic solvent. So when you use those, they prefer SN2. And these solvents, you will see them in the questions and the quizzes. And we use those acronyms. The acronym for those long names of organic compound. DMSO, dimethyl sulfoxide. Okay, this is DMSO. It's a polar aprotic solvent. Acetone nitrile, it has a cyano group, and it's very, very polar too. This is a very polar solvent, acetone nitrile. DMF, a dimethyl formamide, because this is the amide group, and this is the amine. It's very polar. Okay, it's very polar solvent. So these polar solvent, the proton cannot dissociate into the hydrogen cannot dissociate the proton, so they are aprotic solvent. HMPA, the hexamethylphosphoramide. This is the another very polar solvent. These polar solvents are great for substitution reactions, but they are really preferred in the SN2 reaction. And the SN2 reaction, which means strong nucleophiles, and they such a solvent, only the anions, which is the nucleophiles. Okay. The anions are not stabilized by those solvents. the anion not being stabilized by the solvent. So keep in mind, deal with solvent. When you see the reaction conditions, typically is under the arrow. Okay, when you see the reaction, it typically shows down like this. You have the main reagent, for example, this is nucleophile, and the solvent will put under the arrow as a DMF. This is going to be the SN2 reaction, and the stereochemistry will have the inversion. If a reaction uses the alcohol or water as solvent, you see the racemic. Okay, this is the SN2 inversion reaction, SN2. And with the different solvent, the protein solvent will favor the SN1 reaction. The product will be racemic. You got both RS. If your reactant start from one of the RS reactant, the end of the reaction, you get a racemic because the carbocation as an intermediate allow the nucleophile attack from both ends, both sides. So that's the solvent affect SN1 or SN2 mechanism. And that's when you draw the arrows, like I showed you in the class last week, last time. I showed you numerous reactions, how the arrow pushing start ends. And those solvent, it help you decide which way is going. It's SN1 or SN2. It's kind of a side note. When you draw the arrow pushing the reaction steps for the organic chemical reactions, the SN1 tend to have more steps. SN2 tend to have 1 or 2 steps. The very original SN2 reaction is 1 step. But if you consider the last lecture, we go over the alcohol, primary alcohol react with hydrochloric acid or hydrobromic acid, form the alkyl bromide, alkyl halides. Such reaction need 2 steps to convert to halides. But that's still the SN2 reaction. SN2 reaction have a fewer steps than SN1. SN1 minimal 2 steps. It can have as many as 4 steps. Let's show you the last time. So review the last lecture showing those main steps. You see those kind of questions in the quiz and test. So a protein solvent favor SN2, and such a reaction will have fewer steps. The protein solvent, like alcohol, water, they tend to give you the SN1 reaction. So basically, when you use a solvent, you should be more leaning toward the plan ahead. Should I have a carbocation in the reaction? We have SN1, a polar protein solvent, SN1 mechanism, then you would have the proton, the carbocation in the reaction mechanism.
So for our exam, should we have those structures like memorized for because some of them I didn't know before.
Yeah, so you do the Zapping homework. You see what is required. Not all the formulas, yeah. Like some topic like this slide, it won't be much, but you gotta know. This is actually simpler, easier to memorize because they're all highlights. Yeah, there are a lot of them you need to know, memorize. Not all of them. We don't use all the reagents, but as you see, when you see in the quiz and the Zapping homework, those are required to memorize. You won't be given a list. So like the nucleophilicity, good living group, you will basically we assume you memorize. The living group is based on the acidity of the conjugate acid from those living group. Nucleophilicity is kind of difficult because you can see there are not so much patterns, but it seems like a bigger ion. When the anion is larger, you get a better nucleophile. But that's about it. You kind of have a rough idea. Yep, so remember those through the doing, not so much just look the paper, just stick to your head. by doing? The last one. This is one of the very peculiar things. Solvent can, as we mentioned, the solvent, it can favor the SN1 or SN2, depends on what kind of solvent. Here is more dramatic. The protein solvent, it can even change the relative reactivity of the halides as a nucleophile. When you have halide and nucleophile, the solvent can even affect the relative reactivity. And this is people find out from the kinetics research of those substitution reactions. Because we found out in the protein solvent, like in water, alcohol, the reactivity is highest for the iodide. Fluoride is weakest. Main reason because polar protein solvent, you have this kind of bonding, and the fluoride can form kind of hydrogen bonding. If you remember the hydrogen bonding, it bonds very tight with the hydrogen, so that really affects its ability to react. So basically, fluoride being stabilized by the solvent make them not so reactive. And the halides, the iodide, if you remember, iodide is one of the strongest nucleophile in the protein solvent. It's large, and the solvent will not do much with this big ion. It's basically the large halides can have more free and not so much bound by the solvent to react. And in the polar aprotic, DMF, acetonitrile, and so forth, those solvent, it is just complete reversed. The fluoride becomes the most reactive. And so in this case, it's kind of steric effect. It is size of particle, size of the reagent or substrate affect the reactivity. It's completely reversed in the aprotic solvent. And so basically, this part, nucleophilicity, it is measured by the reaction rate. So in the polar protein solvent, iodide reacts fastest. Fluoride is essentially not reacting because fluoride is a poor nucleophile in the aqueous, in the protein solvent. But in the aprotic solvent, fluoride reacts the fastest, and iodide will be slow. So you will see this kind of questions in the Zapping and in our quiz. Not the major topics in this chapter, but we need to be aware of. Solvent can really affect the SN1, SN2, and also affect the reaction rate.